Now I give you Professor Brian Schmidt.
Well, thank you, everyone. And first of all, congratulations to our absolutely outstanding winners today, recognizing the work you and your colleagues have done. Congratulations once again. And thank you to the Infosys Foundation for being prepared to back the foundational academic work occurring here in India and abroad that is changing the way we see the world and ultimately leads to the human progress that each of us wants. And I'm going to be talking about that today in the virtuous cycle of science, because I think it is very easy to forget about how the world of science works and contributes to global prosperity. So I'm going to start at the very beginning. I'm an astronomer. Astronomy is, in some sense, the most abstract and seemingly useless of the physical sciences. Yet it is the oldest physical sciences. In Australia, the Aboriginal and Torres Strait Islander people have a story, the story of the Seven Sisters, story of 6 women and 1 woman gone rogue, stolen by another star. And they use this story to figure out how to navigate the Australian continent. But this story, of course, is a story that we see around the world. It is a story that we see in the stars, the Pleiades, a set of stars 80 million years old, right at the celestial equator. So everyone in the world who has ever existed has been able to see this set of stars. And that's why I think that's an interesting story, because everyone has seen these stars from the dawn of humanity, and we all have stories. In Greece, the Pleiades; here in India, a story. One's in Thailand. We see it in North America. We see it in almost every culture, a version of this story. And the reason is this is a story that predates modern boundaries of countries. It goes back to 65,000 years, because that is the time that the Australian Aboriginals became disconnected from the rest of the world. And yet we have that same story. It is a story that is as old as we can imagine, as old as humanity itself. And indeed, every human has shared and continues to share the stars. This is a very famous cave in Lascaux in France. It's dated very accurately to 17,300 years ago. And you can see the Pleiades next to Taurus, a bull. And why are they there? Well, because when you look in the sky, that is Taurus, the constellation, with Pleiades sitting there on its shoulder. The idea of the constellation of Taurus is 17,300 years old at least. We see it there in that cave. Astronomy has been at the progress of humanity. It has been used to understand when to plant, when to move. But we think of it, I think, most recently over the last 2,000 years of the development of technology. So Ptolemy went through and derived a very elaborate system, the Ptolemaic system, to go out and figure out how the stars and planets were related, how the planets moved across the sky. And he became very good at making predictions. Now, those predictions were based on what the Greeks called axioms, things they took to be true. And axioms are great when they are correct. And in this case, they weren't correct, and so they had to kind of fiddle with the data. But effectively, it was taken that the Earth was at the center of everything, and that everything traveled in circles. And they were able to build up, effectively, this complex set of epicycles that was extremely accurate at predicting where the planets would be over time. And it was so accurate, it stayed put throughout, literally for 1,500 years in place. It was superseded eventually, not actually by Copernicus. He very famously said, this would all be so much simpler if I put the sun at the center, still had everything travel as circles, and it gives you most of what Ptolemy had predicted 1,500 years ago. But it was heretical, because that axiom of the Earth not being at the center was taken away. So it wasn't really thought as being the correct idea until the basics of science started to develop. And that started with, I think more than anyone, Tycho Brahe. And Tycho was, as I think Sri Kulkarni described earlier, someone who just went out and looked at things and measured them. He built elaborate equipment that allowed us to measure very accurately how the planets moved across the sky. He didn't really know why he was doing this, as near as I could tell, but it seemed like something to do up in Sweden in the dark winters. He employed a mathematician of a sort, Kepler, when he was actually forced out of Sweden down into Prague. And Kepler was able to go through and start seeing patterns in what Tycho Brahe saw, because Tycho Brahe had measured the motion of the planets so accurately they could see the large flaws that were in the calculations done using the Ptolemaic system. He could also go through and very cleverly do triangulation on the orbit of Mars. And he soon realized that Mars moved not in a circle, but in an ellipse. Other observations came from Galileo. Galileo had sort of improvised how to use glass optics to make a telescope. And he wasn't really the inventor of the telescope, but he made it practically useful, and he used it to look at the sky. And so when he looked at Jupiter, what did he see? He saw something that looked kind of like this, a big blob that was not a star, but with 4 moons that clearly orbited Jupiter, not the Earth. Clearly the Earth was not the center of that. Heresy, yes, and it cost him dearly. When he looked at Venus, he could see that Venus went, as Copernicus would say it would, from a crescent to full, with the full Venus on the other side of the sun, and the crescent Venus being very close to the Earth, just as Copernicus would say. Galileo really started a theme that lives in science today, which is that when you put down axioms, you test them, and you see whether or not the basics of your theory is actually real. As I said, it cost him dearly. He was put into a very nice Tuscan villa, not allowed to leave it, where he became a winemaker, but probably drank more of his wine than he should for the last 20 years of his life. Newton, well, Newton was the person who really used mathematics to tie all this astronomy together. He built up the theory of gravity, and optics, and a whole bunch of other things. And from that, he could see, emerging from his theory of gravity, that planets and other things should travel on ellipses, just like Kepler realized observationally. He, through calculus, created a powerful mathematical framework where you take ideas and you rigorously test them and help build up what is the scientific method that we use today. Telescopes continued our discovery, and in 1781, using a very large but quite primitive telescope, Herschel was able to discover the first planet that had not been known since historic or prehistoric times. And he did that by just literally a brute force looking across the sky and seeing a disk, a very small, faint disk, move across the sky. This is the planet Uranus. And Uranus was interesting because as they followed it over time, it didn't follow the Newtonian orbit. That is, it seemed that there was a problem with Newtonian physics, unless there was another planet. And Laureate, a French mathematician, predicted through a very impressive set of mathematics for the time where the new planet would be to cause Uranus's track around the sun to make sense. He essentially published that idea, and Galilei in Berlin promptly went out and looked and discovered Neptune just within a year later. Leverrier also noticed that Mercury was moving not as, again, Newton's laws would predict. Its orbit was precessing, and he hypothesized there must be a planet, Vulcan, very near the sun. Now, people looked for Vulcan, and they never could find it, and this was a mystery. It was a small perturbation, but the beautiful thing of Newton's powerful framework of science is when Newton predicted something, he predicted it pretty much exactly to be right. And when you could measure something to be wrong, you knew there was a problem. Unrelated to this, but very important, Einstein was trying to understand a revelation that he had that acceleration and gravity must be indistinguishable. He had this revelation, maybe apocryphally, when he saw someone fall off the roof of a two-story building. And he thought, rather than maybe I should call an ambulance, that that person must not feel any gravity as he falls. That is, that gravity must counteract his acceleration due to falling. And he thought that must just be a foundation that is always true. So the idea is that according to Einstein, you cannot actually tell if you're being accelerated by gravity on Earth or you're in a rocket in space accelerating at the same rate as Earth's gravitational acceleration. It took him 8 years to reconcile that idea. And in the end, he predicted that space should be curved, and that when you looked, for example, at stars near the sun, the curvature of space would cause them to be displaced. He predicted something, people went out and measured it, and found that he indeed was correct. And this was the thing that really made Einstein famous to the average person, because when this eclipse expedition went out by Arthur Eddington and vindicated him, it was one of the first times, except for, I think, Copernicus, where someone went out and made a prediction based on aesthetics. They say, this is a beautiful theory, therefore it should be correct. Now, it turns out science doesn't work that way very often. It has worked with Copernicus saying, I think this is more beautiful, but no reason to make the sun at the center, except for it's more beautiful. And Einstein thinking, aesthetically, I think gravitation and acceleration must always be equivalent. Normally, we have to go out, find a problem, and fix it. Now, it turns out Einstein's theory did fix a lot, and it predicted a lot of things, which we have just, even as of 10 years ago, made a discovery in the case of gravitational waves for the first time, that these things existed. So it's an incredibly powerful theory that we continue to test. So astronomy is the essence of science. It is at the center of the development of the scientific philosophy, where you come up with an idea, you predict things, you observe them, you compare, and then you either modify your theory or you say, well, we think that must be right. And the beautiful thing of this is that it actually allows you to predict things in advance with a great deal of fidelity once you have done enough work to get down to a basic physical theory that actually mimics the real thing. It's not necessarily perfect. Newtonian physics was not perfect, but it was very good. This is foundationally different than something like artificial intelligence, which interpolates on known information. But artificial intelligence, at least to this point, doesn't predict things out of the bounds of our current knowledge, where physical theory does, and it's an important distinction. So now a little bit of a personal story. Here I am with my dad at the age of 5. I grew up in a very remote part of North America. This is Montana, where it is currently 40 below zero Fahrenheit or Celsius. And because that wasn't cold enough, I moved to Alaska. Here I am as a 15-year-old with my first telescope. The problem with the telescope in Alaska is it doesn't get dark during summer. It only is dark during the middle of winter. So I tended to use it to take pictures of animal life more than anything up in Alaska. But the beautiful thing of the way science works is I was able to go from those very remote parts of America and study, first at Arizona, then at Harvard, cosmology, and become an astronomer. And one of the things that I was taught was about the beginnings of cosmology, and Edwin Hubble going out and measuring the distances of stars based on how bright they were, and the fact that the further away the stars were, or the galaxies were, that the stars resided in, the more that their light was redshifted, was stretched. And so this was something that was used to infer that the universe was expanding. And the reason, using a cartoon, that Hubble made that claim was that if you take a universe, and here's a little cartoon universe, and I've expanded it there, and we overlay the first image with the second image, then you see that when you look at nearby objects, they haven't moved much. But when you look at distant objects, as I hope I can show you in a second, when you look at distant objects, they've moved a lot more. And so in a universe that's expanding, you see what Hubble saw. The further away something is, the more it has moved away or its light has been stretched. And so that turns out to actually naturally come out of Einstein's theory of general relativity, although it took a couple decades to realize it. So in the universe, as I learned, when I go through and I look at a distant object, its light travels through an expanding universe and it gets stretched. And the further I look away, well, I'm looking back in time because light travels at a finite speed, 300,000 kilometers per second. But if I look back far enough, I can literally look billions of years into the past. The other thing that I learned using general relativity is that if we go through and we think about the universe and do a thought experiment, if the universe is expanding, we can run it in reverse and think, well, what happens? Well, things get closer and closer in the past, and there is a time in the past where everything is on top of everything else. The Big Bang naturally comes out of that. And so if you go through and do a very simple version of what general relativity predicts, you can go through and say, if I extrapolate back in time, then there is a time of the Big Bang when everything is on top of itself. And all I have to do is go through and measure how fast the universe is expanding now. That's the slope of that line, and I can figure out the age. But general relativity tells you it's not quite that simple. The universe is actually full of stuff, and so gravity, the stuff in the universe, is actually going to slow the universe down over time. And so you actually need to understand how fast the universe is slowing down to figure out how old it is. And general relativity, remember, allows you to predict what happens in the future. And so if the universe isn't slowing down much, it just gets bigger and bigger, it goes on forever. But if the universe is heavy, it might slow down enough so that although all universes start that Big Bang to begin with, only the heavy ones, the ones that got a lot of gravity, slow down in the Big Bang backwards, also known as the Gnab-Gib in certain quarters. So that was what I did for my PhD. Here I am with my PhD supervisor in 1993, very enthusiastically showing Bob Kirshner how fast the universe was expanding. And the number we got, well, the universe is about 14 billion years old. That turns out, I get some credit because that's about the correct answer. And it was a very contested thing that a lot of other people worked on. I can see Shri rolling his eyes and saying, "You got lucky, kid," because many, many people got that answer wrong, but at least I did get it right. So my job was to go through and to think, well, actually, I want to know how old the universe really is and what the future is, and so I need to measure how much the universe is slowing over time. And so you could do another thought experiment, is you look at really, really distant objects, measure how fast the universe is expanding in the distant universe, so that's the past billions of years, and compare it to the present, which is what I did for my PhD thesis. And in this thought experiment, if the universe was expanding faster in the past and slowed down a lot, that yellow line, then you know the universe is heavy and it's eventually going to end in the Gnab-Gib. If it's going slower than that, if it's slowing down slower than that, gravity loses and the universe lasts forever. So that was my pitch to get my first job in Australia. Now to do it, you have to go out and measure distances on the other side of the universe. A team in Chile had figured out how to measure it using exploding stars distances very accurately. So we used them and we started a big experiment. And 3 years and a bit later, we made our measurement. And here is that set of curves, except for there was a problem. When we looked at the distant objects, they weren't slowing down at all. They were above the line. The universe was actually speeding up. That is, we expected a prediction from general relativity. General relativity told us the wrong answer, seemingly. Well, it turns out general relativity is a little complicated. And so we discovered that the universe was accelerating, a big surprise for which a team, myself included, and 20 people from 5 continents were part of. Well, that was a huge surprise. That is why we won the Nobel Prize. Now, it was about being at the right place at the right time with people's work for hundreds of years, going right back to Newton. That's what allowed us to do this work. And that's the way science works. The one thing, since we have a number of young people here, in 1998, when we made this discovery, there were not a lot of women in astronomy, as you can see. Since that time, half my students, half my postdocs have been women. So if you are a young woman, take solace, it's a lot better, and we've made some practice, lots of room for astronomy for you. So our discovery is part of that evolution of how science works. Now it turns out we think that actual general relativity is right, because Einstein realized back in 1917 that if the universe is full of energy, it will naturally accelerate, as we discovered. We had no reason to believe the universe was full of energy. But even to this day, 2024, more or less, the ideas behind our experiment in 1998 hold true. There are a few creeping little issues that we need to understand, but the basic story remains as it was 20 years ago. At this point, my minister of science and industry, emphasis on industry, comes and says, "Why do I care?" And this is when I have to actually talk about how science works. Because as we go out and do work in science and astronomy and astroparticle physics, the area that I work in, seemingly the most useless area of science, it ends up making a difference. So let's look at our iPhone or Android phone, and you realize that we have all sorts of things in there that depend on the astronomy I do. The GPS systems use general relativity. The Wi-Fi was actually invented by Australian astronomers working in the area of pulsar bits. The CMOS camera that we all use to post on Instagram, well, that was developed by JPL for a mission to Jupiter. And the touchscreen was invented in CERN. Indeed, if you go through and look, for example, at just the CMOS camera, it's a fairly recent invention. And this goes back to 1992, and now we have them in literally billions upon billions of devices. It's a revolution that occurred because astronomers needed it to occur to get a low-energy device to Jupiter that we could run. And this is true of almost everything that is in the iPhone. If you look at all the pieces of an iPhone, these are all the basic scientific discoveries going back in time all the way to the Greeks and before that have led to that. And that is, if you really want to know, just the tip of the iceberg of what goes in. Technology is complex. When the minister says to you, but why don't you just give me the iPhone and don't do all the science? The answer is the ideas come from the basic research that we are celebrating with our winners tonight. So much to do. What should we be working on? Well, I personally am going to be working on what's going on with black holes. There are many, many of them, and they're big. And we're using laser interferometers to measure one of the predictions of general relativity, that there will be gravitational waves. And a gravitational wave is emitted when, for example, two black holes, also predicted by general relativity, come together, and they create a little ripple in space where at some point, when one of these comes through you, your head gets a little bigger this way, then a little bigger this way. And if you can measure things to about 1,000th the width of the atomic nucleus, then you can actually see these. And it turns out that technology exists to that level of accuracy through the LIGO experiment, now the Virgo experiment, and other experiments, including, we hope, an experiment here in India I'll talk about just briefly. But what we're finding is throughout the universe, black holes are coming together and forming large black holes. But what's interesting is the universe is full of black holes that are 20, 30, 40, 50, even 100 times the mass of our sun. And we just don't see those. Now, it turns out they're actually quite hard to see. Black holes have the name they have for a reason. But it is, I would say, maybe a little bit of a surprise that there are so many black holes of that size. And it's telling us that perhaps black holes were created en masse in the early universe. And the first things that we're seeing from the James Webb Space Telescope perhaps are giving us hints. And some of the metal-poor stars, those are the first stars in the early universe, also suggest this. That's some other work that I have done. But we want to go out and we want to look at these things in detail and go through and understand in detail how the black holes were created back in time. So that is something I will be working on in the years to come. And India, I believe, will be working on it as well. Because LIGO India is a big project going on here and getting started, where we are able to put one of these very precise laser interferometers in India to help us measure much more accurately in the sky where these things occur, and also give us a higher ability to detect them. Now, LIGO itself, you would say, again, why would India do this? Well, it, again, is a bleeding edge technology. And ANU, my university, has been in the middle of helping create the very precise detectors over the last 20 years. And just in the last 3 years, I've had the chance last year when Prime Minister Modi visited Australia to talk about this, and he wanted to talk about LIGO India in his visit to Australia. So that's what we're talking about here. And here at ANU, we have been able to use some of the fancy quantum squeezing, where we're able to extract more information to go out and create very precise LiDAR and create spin-out technologies that are going to help everything from agriculture to defense. We have another spin-out called Liquid Instruments that uses the technology behind LIGO to create precision testing equipment that's used in the new rounds of electrical equipment in all sorts of ways. And we have another spin-out that has just come out, again, out of our very small group that works on LIGO-type things at ANU. Because that basic science creates the ideas that are then translated. So that's why India is probably going to work on LIGO, is to help create that technology and scholars who have that knowledge to go out and do everything from spin-outs to helping the existing companies go out and remain at the cutting edge. So it is an exciting time to be doing science. Things like the James Webb Space Telescope, the biology revolution that we've heard about, how we're able to go through and do precision experiments in biology and chemistry. But the science and technology we do are completely interdependent these days. One makes the other, makes the other. And so to our young students in the audience, if you love science, it's something really worthwhile doing. It's not just a gateway to the knowledge, but it's a gateway to the world of technology and startups. And so I encourage people to have the confidence to do the science like our winners tonight, because it gives you a range of options, a range of things to do no matter what we do in the years ahead. As you study to these young people, I always tell people to make sure you learn to do something that you love so you do it well, because it gives you the ability to go through and learn how to learn and learn the deep skills required to do something well. And that quality, that capability, is what you can turn into almost any problem. It's a way of thinking, it's a way of learning, and a way of doing that is incredibly powerful and underpins the technological revolution that powers humanity. And so to people I say, don't be scared to use that knowledge to whatever comes in front of you, because you will have so many options if you have that deep ability in science and technology. And this is important because the future is for humanity to make. In this picture taken about the time I was born, you can see Australia and India about a quarter of the globe apart. There are 8.1 billion humans on this earth, growing at about 70 million humans per year. And we are in a race to ensure that humanity can peacefully coexist on planet Earth while we develop the technology that underpins energy transitions, food transitions, water transitions. And that is going to be done, that knowledge is going to be done by basic science feeding into technology in that virtuous cycle. That is the future of a prosperous humanity. Thank you, everyone.